US Physics Olympiad year 2018 final round USAPHO. This examination consists of two parts. Part A has 3 questions and is allowed 90 minutes. Part B also has 3 questions and is allowed 90 minutes. Problem A1. Question A. Suppose you drop a block of mass m vertically onto a fixed ramp with angle theta with a coefficient of static and kinetic friction μ. The block is dropped in such a way that it does not rotate after colliding with the ramp. Throughout this problem, assume the time of the collision is neglectable. First, suppose the block's speed just before it hits the ramp is v and the block slides down the ramp immediately after impact. What is the speed of the block right after the collision? Second, what is the minimum μ such that the speed of the block right after the collision is 0? Question B. Now suppose you drop a sphere with mass m, radius r and the moment of inertia beta m r square vertically onto the same fixed ramp such that it reached the ramp with the speed v. First, suppose the sphere immediately begins to roll without slipping. What is the new speed of the sphere in this case? Second, what is the minimum coefficient of friction such that the sphere rolls without slipping immediately after the collision? Solutions for problem A1. Part A. During the collision, the block receives impulses from the normal force, friction and gravity. Since the collision is very short, the impulse due to gravity is neglectable. Let Pn and Pf be the magnitudes of the impulses from the normal force and the friction force. Since the block stays on the ramp after the collision, its final momentum is parallel to the ramp. Then the normal force must completely eliminate the block's initial momentum perpendicular to the ramp. So we have Pn equal mv cosine theta. Since the block still moves after the collision, we have Pf equal mu Pn or mu mv cosine theta. The block's initial momentum parallel to ramp is mv sine theta. So we have mu equal mv sine theta minus mu mv cosine theta, or velocity equal v multiplied by sine theta minus mu cosine theta. Second, we have to set u equal 0. It means that mu equal tangent theta. Note that this is simply the no-slip condition for a block resting on an inclined plane. This is because in both cases equality is achieved when the normal force and maximal friction force sum to a purely vertical force. Question B. Now suppose you drop a sphere with mass m, radius r and the moment of inertia beta m r square vertically onto the same fixed ramp such that it reached the ramp with a speed v. I. Suppose the sphere immediately begins to roll without slipping. What is the new speed of the sphere in this case? Here, because we have no slipping after impact, we have angular momentum conservation around the point of contact. It means that initial angular momentum, which is mvr sine theta, equal final angular momentum, which is m multiplied by moment of inertia around this point, which is beta m r square plus r square due to parallel axis theorem, multiplied by omega, which is angular velocity of rotation. And because we don't have slipping, we have omega equal Vx over r. From here we can find what is horizontal speed of the sphere, Vx, which is v sine theta over 1 plus beta. Second, what is the minimum coefficient of friction such that the sphere rolls without slipping immediately after the collision? As in part A, because we have a change of normal impulse is mv cosine theta, and the change of horizontal momentum is mu multiplied by p normal, we have f horizontal equal mu mv cosine theta. But from other hand, that's equal to initial horizontal momentum minus a final horizontal momentum, which is this expression, or change of horizontal momentum equal mv beta sine theta over 1 plus beta. Using this equation and this equation, we can find what is minimum possible coefficient of friction. That will be beta tangent theta over 1 plus beta. That was a solution for problem A1. Problem A2. For this problem, graphical answers should be drawn on the answer sheets, graphs provided. Supporting work is to be written on blank answer sheets. Incorrect graphs without supporting work will receive no partial credit. The current I as a function of voltage V for a certain electrical device is next one, where Q is the magnitude of the charge on an electron, QB is Boltzmann's constant, and T is the absolute temperature. I0 and V0 are non-zero positive constants. Throughout this problem, assume low temperature values KBT much less than QV0. Question A. On the answer sheets, sketch a graph of the current versus voltage for low temperature values KBT much less than QV0, clearly indicating any asymptotic behavior. Solution for problem A2. Question A. The current is simply proportional to this expression, which is shifted exponential. Then I always has the same sign as V, and vanishes when V vanishes. The current grows quickly for high V and approaches zero for low V. This answer is acceptable, but we can use the condition that KBT much less than QV0 to simplify the graph. For negative V, we have I over I0 approximately equal negative E in power this one, which is extremely small. For positive V, we have I over I0 approximately equal this expression, which is extremely small when V less than V0 and extremely large when V greater than V0. Then we have this answer. Accounting for finite temperature, which is not necessary for full credit, simply rounds the corners in all of the graph. And the final graph should look like this. This is answer for question A, and this was the solution for this question. Shown is a schematic for the device. Positive voltage means that the electric potential of the left hand side of the device is higher than the right hand side. For this device, I0 equal 25 microampere and voltage and V0 equal 1 volt. Below is a circuit made up of these elements. The voltage supplied the circuit is sinusoidal. VAB equal VA minus VB equal Vs sine omega t, and is also shown on the answer sheet. The resistance is R equal 5 ohm and the S equal 5 volts. Question B. Sketch the potential difference VCD equal VC minus VD as a function of time on the answer sheet. For your convenience, VAB is shown in light gray. Assume that VAB has been running for a long time. So that's the answer sheet. Solution for question B. When absolute value VAB less than 2 V0, no current flows. When absolute value VAB greater than 2 V0, current begins to flow, which with each diode subtracting a potential difference of V0. Note that the current flows in the same direction for both positive and negative VAB. This device is a rectifier. Now a capacitor is connected to the circuit as shown below. The capacitance is 50 microfarad. Question C. Sketch the new potential difference VCD equal VC minus VD as a function of time on the answer sheet. For your convenience, VAB is shown in light gray. Assume that VAB has been running for a long time. So that's the answer sheet. Solution for question C. Let the voltage on the capacitor be Vs whenever absolute value for VAB greater or equal to Vs plus 2V0. Current flows through the diodes, charging the capacitor up to voltage absolute value VAB minus 2VA0. Whenever absolute value for AB greater or equal to Vs plus 2V0, no current flows through the diodes, and the capacitor and the resistor simply discharge as an RC circuit with time constant equal to 250 milliseconds. Since RC is much longer than the time scale on the answer sheet, the discharge is approximately linear, with dVs over dt equal to 1 volt over 83.3 milliseconds. Thus, the capacitor charges completely to 3.0 volt every cycle, then discharges approximately linearly by about a half volt during the remainder of the cycle. On the graph, we show charging as red and discharging as blue. So that was a solution for question C, and that was problem A2. US Physics Olympiad, year 2018, USA, PHO. Problem A3. A vacuum system consists of a chamber of volume V connected to a vacuum pump that is a cylinder with a piston that moves left and right. The minimum volume in the pump cylinder is V0, and the maximum volume in the cylinder is V0 plus delta V. You should assume that delta V much less than V. The cylinder has two valves. Inlet valve opens when the pressure inside the cylinder is lower than the pressure in the chamber, but closes when the piston moves to the right. The outlet valve opens when the pressure inside the cylinder is greater than atmospheric pressure PA, and closes when the piston moves to the left. A motor drives the piston to move back and forth. The piston moves at such a rate that heat is not conducted in or out of the gas contained in the cylinder during the pumping cycle. One complete cycle takes time delta t. You should assume that delta t is a very small quantity, but delta v over delta t equal r is finite. The gas in the chamber is ideal monatomic and remains at a fixed temperature of Ta. Start with the assumption that V0 equals 0 and there are no leaks in the system. Questions. Question A. At time t equals 0, the pressure inside the chamber is Pa. Find an equation for the pressure at later time t. Question B. Find the expression for the temperature of the gas as it is emitted from the pump cylinder into the atmosphere. Your answer may depend on time. For the remainder of this problem, 0 less than V0 less than dV and much less than V. Question C. Find an expression for the minimum possible pressure in the chamber P minimum. Solution for the problem. Question A. At t equals 0, the pressure inside the chamber is Pa. Find an equation for the pressure at a later time t. Solution. During each cycle, the system sucks gas out of the chamber and pushes it into the atmosphere. Since V0 equals 0, the inlet valve opens the moment the piston starts moving to the left. When the piston is all the way to the left, a fraction of delta V over V plus delta V of the gas is in the cylinder. As the piston moves to the right, all of the gas is pushed out, so after a single cycle, we have P final equal P initial multiplied by V over V plus delta V. And in general, P is a function of T equal PA multiplied by V over V plus delta V in power of T over delta T. While this is technically correct, it can be simplified significantly. P as a function of T in form of this one or this one, where x equal delta V over V, which is much less than 1. Then using the definition for exponent, as such limit, we have P as a function of t equal PA multiplied by exponent in power of negative RT over V. That was a solution for question A. Question B. Find an expression for the temperature of the gas as it is emitted from the pump cylinder into the atmosphere. Your answer may depend on time. Solution. When the piston is all the way to the left, the pressure is Pt and the temperature is Ta. As the piston moves to the right, the gas is adiabatically compressed until its pressure reaches Pa, and the outlet valve opens. Since PV power gamma is constant during adiabatical process and the PV over T is constant by the ideal gas law, we have T out is equal to this expression, and because for monatomic gas we have gamma equal 5 over 3, and question answer, we have this answer for question B, that T out equal Ta multiplied by exponent power 2RT over 5V. So that was a solution for question B. Question C. Find an expression for the minimum possible pressure in the chamber, P minimum. Answer. Since V0 greater than 0, the inlet valve will not open immediately when the piston begins moving to the left. Instead, it will open once the pressure in the cylinder equals the pressure in the chamber. Since the expansion of the cylinder is adiabatic, we have PV power gamma is a constant, so P minimum equal PA multiplied by this expression or this formula. That was answer for question C, and that was answer for all three questions for problem A3. US Physics Olympiad, year 2018, USAPHO. Problem B1. The electric potential at the center of a cube with a uniform charge density ρ and the side length A is approximately 0.1894 ρ A square over epsilon 0. You don't need to derive this. For the entity of this problem, any computed numerical constants should be written to 3 significant figures. Question A. What is the electric potential at the corner of the same cube? Write your answer in terms of ρ A, epsilon 0 and any necessary numerical constants. Question B. What is the electric potential at the tip of a pyramid with a square base of side length A, height A over 2, and the uniform charge density ρ? Write your answer in terms of ρ A, epsilon 0, and any necessary numerical constants. Question C. What is the electric potential due to a square plate with a side length A of a uniform charge density sigma at a height 8 over 2 above its center? Write your answer in terms of sigma A, epsilon 0, and any necessary numerical constants. Question D. Let E as a function of Z be the electric field at the height Z above the center of a square with a charge density sigma and the side length A. If the electric potential at the center of the square is approximately 0.1281 A sigma over epsilon 0. Estimate A on distance A over 2 by assuming that E from Z is linear in Z for 0 less than Z less than A over 2. Write your answer in terms of sigma A, epsilon 0 and any necessary numerical constants. Solutions for problem B1. Question A. What is the electric potential at the corner of the same cube? Write your answer in terms of rho A, epsilon 0 and any necessary numerical constants. Solution. By dimensional analysis, potential equal approximately C rho A square over epsilon 0, where C is some kind of dimensionless constant. Note that the cube of side length A consists of 8 cubes of size length A over 2, each with a corner at the center of the larger cube. Then we have this equation. So from here we can see that constant C equal this expression 0.0947. So the answer will be this one. Question B. What is the electric potential at the tip of a pyramid with a square base of side length A, height A over 2 and the uniform charge density rho? Write your answer in terms of rho A, epsilon 0 and any necessary numerical constants. Solution. A cube of side length of A consists of 6 such pyramids. Then we simply compute that constant C equal 0.0316 and potential for pyramid equal this expression. Question C. What is the electric potential due to a square plate with a side length A of a uniform charge density sigma at a height A over 2 above its center? Write your answer in terms of sigma A, epsilon 0 and any necessary numerical constants. Solution. Let the potential due to such a square be this one. Note that adding a square plate of infinitesimal thickness dz and the side length A to a square pyramid with a base side length A and the height A over 2 yields a square pyramid with a base side length A plus 2 dz and the height A over 2 plus dz. The surface charge density of a square plate with a thickness dz and volume charge density rho is rho dz. Then by the principle of superposition we have this expression. And this is the answer for question C. Question D. Let EZ be the electric field at the height Z above the center of a square with charge density sigma and the side length A if the electric potential at the center of the square is approximately this expression. Estimate E in point A over 2 by assuming that EZ is linear in Z between 0 and A over 2. Write your answer in the terms of sigma A, epsilon 0 and any necessary numerical constants. Solution. The potential difference between height 0 and A over 2 is dF equal this one. On the other hand, We approximate Ez as linear by Gauss law in the point E0. We have electric field equal sigma over 2 epsilon 0. And from here we can find that electric field in the point A over 2 equal 0.119 sigma over epsilon 0. This was the answer for question D, and that was total solution for all problem. US Physics Olympiad year 2018 USAPHO problem B2. In this problem, use a particle-like model of photons. They propagate in straight lines and obey the law of reflection, but are subject to the quantum uncertainty principle. You may use small angle approximations throughout the problem. A photon with a wavelength lambda has traveled from a distant star to a telescope mirror, which has a circular cross-section with radius big R and a focal length f much greater than R. The path of the photon is nearly aligned to the axis of the mirror, but has some slight uncertainty delta theta. The photon reflects off the mirror and travels to a detector where it is absorbed by a particular pixel on a charge-coupled device CCD. Suppose the telescope mirror is manufactured so that the photons coming in parallel to each other are focused to the same pixel on the CCD, regardless of where they hit the mirror. Then all small cross-sectional areas of the mirror are equally likely to include the point of reflection for a photon. Question A. Find the standard deviation delta R of the distribution for R, the distance from the center of the telescope mirror to the point of reflection of the photon. Question B. Use the uncertainty principle delta R multiplied by delta P greater or equal to reduced Planck constant over 2 to place a bound on how accurately we can know the angle of the photon from the axis of the telescope. Give your answer in terms of R and lambda. If you were unable to solve part A, you may also give your answer in terms of delta R. Question C. Suppose we want to build a telescope that can tell which high probability whether a photon it detected from Alpha Centauri A came the left half of right half of the star. Approximately how large would a telescope have to be to achieve this? Alpha Centauri A is approximately 4 by 10 power 16 meters from Earth and has a radius approximately 4 by 10 power 9 meters. Assume visible light with a lambda equal 500 nanometers. Solution for problem B2. Question A. Find the standard deviation delta R of the distribution for R, the distance from the center of the telescope mirror to the point of reflection of the photon. Solution. The square of the standard deviation is the variance, so we have deviation delta R square equal average value of R square minus square of average value of R. Mathematically, the exact same thing as computing the moment of inertia of a uniform disk. So it means that average for r square equal this integral, and the average for r is this integral. So it means that answer will be delta r equal r over square root from 18. That was a solution for question A. Question B. Use the uncertainty principle delta r multiplied by delta p greater or equal Planck constant over 2 to place a bound on how accurately we can know the angle of the photon from the axis of the telescope. Give your answer in terms of r and lambda. If you were unable to solve part A, you may also give your answer in terms of delta r. Solution. We have delta pr approximately equal to p multiplied by delta theta, which is equal to h over lambda multiplied by delta theta. Applying the uncertainty principle, we have delta theta greater or equal to square root from 18 lambda over 4 pi r. Since the factor of h cancelled out, this is really a classical calculation. One could get a similar result by considering classical diffraction from a circular aperture. Question C. Suppose we want to build a telescope that can tell which high probability whether a photon it detected from Alpha Centauri A came the left half of right half of the star. Approximately how large would a telescope have to be to achieve this? Alpha Centauri A is approximately 4 by 10 power 16 meters from Earth and has a radius approximately 4 by 10 power 9 meters. Assume visible light with a lambda equal 500 nanometers. Solution. We need delta theta to be much smaller than the actual angular separation, or delta theta must be much less than 2 by 10 power negative 8. So it means that r must be much greater than this expression, or equal to 8.4 meters. So that's the answer for problem C, and that was a full solution for whole problem B2. US Physics Olympiad year 2018, USA PHO, problem B3. Radiation pressure from the sun is responsible for cleaning out the inner solar system of small particles. Question A. The force of radiation on a spherical particle of radius small r is given by formula F equal PQ P r square, where P is the radiation pressure and Q is a dimensionless quality factor that depends on the relative size of the particle r and the wavelength of light lambda. Throughout this problem, assume that the sun emits a single wavelength lambda maximum. Unless told otherwise, leave your answer in terms of symbolic variables. I. Given that the total power radiated from the sun is given by Ls, find an expression for the radiation pressure at distance r from the sun. II. Assuming that the particle has a density ρ, derive an expression for the ratio F radiation over F gravity in terms of Ls, mass of sun, ms, ρ, particle radius r, and the quality factor q. III. The quality factor is given by one of the following. Consider the three possible particle sizes, which is most likely to be blown away by the solar radiation pressure. Solution for part A. Question I. Given that the total power radiated from the Sun is given by Ls, find an expression for the radiation pressure at distance r from the Sun. Solution. We can use here expression for a formula which connect impulse and energy of one photon. Impulse equal energy over speed of light. The power will be energy over time. So when we summarize all impulses for photons, we will get formula that the total impulse equal total energy over speed of light. And we can assume this formula as this. And the change of this impulse over area, that will be pressure. So we have pressure equal total intensity over speed of light, or power over 4 pi r square c. So that was answer for question I. But alternatively, this relation can be derived using classical electromagnetism, though this was not required. For a plane wave, the momentum density of the electromagnetic field is by this formula, while the energy density is this one, where S is a Poynting vector, like this. So we have pressure equal intensity over speed of light, because c square equal 1 over epsilon 0 mu 0. That's answer for question I. Question II. Assuming that the particle has a density ρ, derive an expression for the ratio F radiation over ray F gravity in terms of Ls, mass of Sun ms, ρ, particle radius r, and the quality factor Q. Solution. Force of gravity equal this expression. Force of radiation equal this expression. So we have relation. And finally, ratio F radiation over F gravity equal this expression. That was answer for question 2I. Question III. The quality factor is given by one of the following. Considering the three possible particle sizes, which is most likely to be blown away by the solar radiation pressure. Solution. In order to be blown away, the ratio should be greater than 1. Since it is independent of distance from the Sun, if it is blown away, it will be blown away at any distance. For r much greater than lambda, the ratio is proportional to 1 over r, so smaller particles are more likely to be blown away. For r much less than lambda, the ratio is proportional to r, so large particles are more likely to be blown away. Thus, particles of size near lambda are most likely to be blown away, and even then, only if the density is small enough. That was answer for problem B, part A. Part B. The Poynting-Robertson effect acts as another mechanism for cleaning out the solar system. I. Assume that a particle is in a circular orbit around the Sun. Find the speed of the particle v in terms of ms, distance from Sun r, and any other fundamental constants. II. Because the particle is moving, the radiation force is not directed directly away from the Sun. Find the torque tau on the particle because of radiation pressure. You may assume that v much less than speed of light c. I. Since tau equal dl over dt, the angular momentum L of the particle changes with time. As such, develop a differential equation to find dr over dt, the rate of change of the radial location of the particle. You may assume the orbit is always quasi-circular. I4. Develop an expression for the time required to remove particle size r about 1 cm and density 1000 kg per meter cubic, originally in circular orbit at a distance r equal r Earth, and as numbers below to simplify your expression. Some useful constants include solution for questions in part B. Assume that a particle is in a circular orbit around the Sun. Find the speed of the particle v in terms of ms, distance from Sun, r, and any other fundamental constants. Solution. Using the circular motion equation, we have gravitational force is responsible for centripetal acceleration. So we have this formula, and from here we have speed equal square root from gm over r. That's answer for problem 1 in part B. Question 2 from part B. Because the particle is moving, the radiation force is not directed directly away from the Sun. Find the torque tau on the particle because of radiation pressure. You may assume that v much less than speed of light c. Solution. We work in the reference frame of the particle. In this frame, the radiation hits the particle at angle theta equal v over c from the radial direction. The particle then re-emits the radiation isotropically, contributing no additional radiation pressure. We ignore relativistic effects because they occur at second order in v over c, while the effect we care about is first order. The tangential component of the force is this one. So the torque will be this one. This is the answer for question 2 in part B. Question 3. Since tau equal delta L over delta t, the angular momentum L of the particle changes with the time. As such, develop a differential equation to find dr over dt, the rate of change of the radial location of the particle. You may assume the orbit is always quasi-circular. Solution. By the way, we had a negative sign for torque because this tends to decrease the angular momentum. Solution for question 3. Solution. The angular momentum is this one. Now we can take a first derivative by time from both parts, and we have torque equal dl over dt, or what we did before. It's this one. And with simplifiers to this equation, we have this answer for question 3 part B. This is our differential equation to find dr over dt. So that's answer for question 3 part B. Question 4 from part B. Develop an expression for the time required to remove particle of size r approximately equal 1 centimeter and density about 1000 kg per cubic meter, originally in circular orbits at a distance r equal radius of distance of Earth from Sun, and as the numbers below. Simplify your expression. Some useful constants include these expressions with meaning. Solution. We have a differential equation like this. So if we split expression and after integrating we have time equal this expression. So if we know what distance we have to remove particle from the Sun, we can put it instead of R1 and count what is total time. That's a solution for question 4. And that was a solution for total problem B3.